Alright, so in this tutorial we're going to look at this phenomenon called resonance. In class I showed you a few demonstrations with the crystals that were kind of singing the vibrating of the tuning forks that had the same frequency, and then the singing rod. Resonance is a special case of interference. This is a very, very important phenomenon that occurs in nature. Long story short, resonance is a amplification effect where you get a large amplification or large amplitudes for buildings, for sound, a whole host of things based on interference. So we're going to look at the details of this. There's really not much mathematics involved. It's conceptual, but you understand more than anything the applications. Okay, so let's break it down. We talked a little bit about this class. So when any medium is disturbed, it will oscillate at a natural frequency. So that natural is very, very important. All objects vibrate with certain frequencies based on their structure, their length, and other factors. Okay, so we label the natural frequency. In complex systems like buildings, etc., have many vibrational modes. So it's not like an object has just one natural frequency. It usually has multiples of them. Okay, and the nice example of that is that tinny. All right, that metallic sound of a drop metal rod. We can tell it's metal because of specific frequencies that are on the higher end of the frequency spectrum as opposed to, let's say, wood. All right, now, additionally, the same medium can be forced to vibrate when a driving frequency is periodically applied. So if I've got let's say some water. Water vibrates at a particular natural frequency based on the molecular structure of water and the forces between them. If I keep hitting water, that's a driving frequency. Okay, that's different than the natural frequency at which water vibrates. Another example is those tuning forks. Okay, the tuning fork itself has a natural frequency based on its shape and size. Whereas if I bring another tuning fork near it, which is vibrating, that would be a driving frequency. All right, so we'll make sure we understand the difference between driving frequency and natural frequency. And a really good example is the periodic push of someone on a swing. Okay, in other words, every time you push with a certain frequency. That's a driving frequency. The swing itself has a natural frequency based on its length. Okay, and an important thing about this applied driving frequency, applied force, is it adds energy to the system. So what we want to understand is how you can get more and more energy built up by using little, if you will, little events of adding small amounts of energy to it. Or little increments of energy is what I want to say. So here's the interesting part, and again, we'll go look at a bunch of examples in class. As the driving frequency approaches the natural frequency, in other words, their values get closer and closer, then the amplitude, okay, increases dramatically, and the only limit on how big the wave can get, the amplitude, is the amount of damping in the system. And damping is kind of like something that is like an opposing force, so almost like a friction. If you ever look at shock absorbers damp vibrations in a car when it goes over a bump, so you're not oscillating for a long period of time. But don't worry about this. So just in other words, you can get the amplitude go higher and higher and higher to a certain limit when your driving frequency matches your natural frequency, is very close to it. And this phenomenon is called resonance. Okay, so let me say it again. I cannot overstate this. Resonance is an interference effect where waves meet one another, where I have a wave like this and another wave is matching it, and I get a big amplitude because the timing is right. There's a frequency here, there's a frequency there that match one another. So if we look at this from a graphical standpoint, let's say I have some object that is some driving frequency on it, and we're at some arbitrary driving frequency. The amplitude is moderate, it's steady. Then as we approach, so this dashed line here is, let's call it the natural frequency, Fn. Okay, we'll call it natural. As this approaches, the amplitude will rise very sharply, drop just as suddenly, and then go back to what it was. So in this, don't circle this, but in this zone right here, there's your resonance. You have a large amplification because two frequencies are matching one another. And what we want to understand is how can this be applied in nature. All right, so like I said, I'll show you various things, but let me just fill these in. There's vibrations in bridges and buildings. Okay, a classic example is with earthquakes. When an earthquake hits a building, there are certain frequencies in the earthquake waves. They're very, very low frequencies. If a building has natural frequencies that match some of those earthquake waves, then you can get a resonance which will cause it to sway much more than usual, and that's where structural damage will occur. So for when an earthquake proof a building, we put in certain materials or dampers in that system so that it gets rid of those frequencies that would match those of the earthquake waves. I'll show you another classic example many of you have seen before, is suspension bridges. Okay, so I'll show you a YouTube clip tomorrow. All right, B, microwave ovens. In other words, microwave ovens cook food because of a resonance effect. All right? You have a radiation of a particular frequency. That's the microwaves. All right? We'll talk about what that is later on. And so you have a very specific frequency of those microwaves. If you have a substance that you put in a microwave that has vibrational modes, natural vibrations that match that, then what will happen is the objects or the material that is moving with the same frequency as the microwaves will absorb the microwaves. That's why absorption of radiation occurs, is because we have a matching of frequencies. And if that happens, then if that matches if the frequency of radiation matches that of the vibrations in the food, that causes resonance, thus generating a lot of heat. In other words, if you absorb the microwaves, you are absorbing the energy of it, and that will cause the molecules to jiggle even further. Further means more energy, they get hotter. And the key aspect of the microwaves is water. So it turns out that liquid water has vibrational frequencies that overlap that of microwaves. So liquid water is key to cooking your food. If you were to have solid water, in other words, an ice cube, and you place it in a microwave, it would not absorb any of the microwaves because the molecules of ice, liquid water, do not have the same frequencies of that of microwaves. Okay, so another one we'll show is shattering glass with the human voice. You may have heard of opera singers being able to break glass if they sing high enough. And that's in theory true. If the opera singer hits a high enough frequency that matches one of the vibrational modes of the glass, then you can get an amplification, a resonance, which will cause it to vibrate with a greater displacement than normal, and that can cause it to break. So we'll look at some other things in there. Musical instruments, huge. Okay, the dominant note heard is nothing more than a particular resonant frequency. In other words, anytime you pluck a string in a guitar, you play a note on a trumpet, or hit a xylophone bar, is that note you hear is a amplification of a particular frequency, and that's what we call the note. We'll have much more to say about that. And the last thing we want to know in the environment, that's a big one these days, is called the greenhouse effect. Okay, the greenhouse effect, which is associated with global warming. And the idea is the natural frequency of certain molecules in the atmosphere, namely carbon dioxide and water vapor, happen to be overlap the infrared region of the electromagnetic spectrum. And you might wonder, what's the big deal with that? Well, the Earth basically radiates this. The Earth shines in infrared. And so if we absorb a lot of the infrared trying to escape the Earth, the CO2 and the H2 will kind of act like a blanket. And the reason they act like a blanket, again, is because they have frequencies of vibration that match that of infrared, so they'll absorb infrared. And so if they're absorbing a lot of the infrared that the Earth is trying to radiate away into space to kind of cool off, then it's going to keep us warmer than normal. Okay, so again, resonance is everywhere in nature. I've just given you 5 simple examples, but it's essentially what happens when you have a driving frequency matches a natural frequency. You get a larger vibrations than normal. All right.